And part B looks at connections. And again, a lot of software doesn't design connections. And it's a huge, huge gap in software, particularly in New Zealand. And it's often the weak link. And every structure will fail at its weakest link. So in part B, we'll look at the SCNZ handbook and the Bentley RAM connection software briefly, and we'll go back into MathCAD. I won't bore you too much with MathCAD. I'll just start with one, and then I can point you in the other direction. Okay, so there is a thing you may be familiar with, which is the Steel Construction New Zealand. You'll say yes? You know it? All right. Steel. All right. There's HERA, which is the Heavy Engineering Research Association, and they do big structures and big publications. But for us mere mortals doing buildings, this is one that's more appropriate. This is the Steel Construction Handbook. It was originally all in paper, but they've moved with the times and got an online version. Now, companies joining it pay an awful lot of money. But there is a student membership, but it doesn't tell me how much it is. So if you want to join as a student and get access to their information, you need to get in touch with them directly. So this is their website. Once you've logged in to the page, you can start designing connections. Okay, and the way you do it is you pick out what piece of metal you're using. So typically, in a hot rolled steel frame building, you'll be using universal beams or universal columns. So in this case, I've chosen a universal beam. It's 410 millimeters deep, and it's a 53.7 kilograms per meter. So that's the serial size. What connection am I going to do? Well, there's a very cryptic thing called an AC1-260 SWC. What the hell does that mean? And it's pretty cryptic as to what all those types of connections mean. And you've got to dig deep as to what they do. But if you go to the Daddy Pig YouTube channel, I've explained what each of the type of connections are. By default, it goes for grade 300. Grade 300 is not the only type of steel, but it's one of the more common types of steel for hot rolled steel buildings. It also defaults to grade 250 for the connections. And again, you can use whatever grade you like if you really want to. It's got a design capacity of 370, and it doesn't tell you what the axle capacity is or the moment capacity. So this is just a shear connection. If you click on a certain button, you can get to the output, and it puts out a report like this. On the right, you've got a generic sketch of what it is. On the left, you've got the input you've put in. So it's a member of a grade 300 and 410 universal beam, and you've got an angle cleat. That's what the AC means, an angle cleats, grade 250. And it tells you what the results are. So you're using 8.8 bolts and you're using 20 mil diameter bolts. And I think pretty much every one of their connections uses 8.8 bolts, 20 mil diameter, which is pretty much the standard for hot rolled steel frames. Not cold form steel frame, hot rolled steel frames. And it makes sense because the guys erecting your steel frame will carry around a bag of bolts. And it's very handy if the same bolt applies to every hole. So they don't have to think about which one it is. In the past, they did. And clever engineers thought they were being clever by making all the bolts different. It takes a lot longer to build the damn thing if you do that. It also gives you a generic drawing. So you've got this case, a beam-to-beam connection held together with two angle cleats down the side and bolts joining the two. So you've got 4 bolts basically to the primary member and then 3 bolts to the secondary member that you're doing. So it's not a particularly specialized drawing for your project. It's just a generic which you can use. I want one of these type of joints. And if you can put that in your calculations and you can put it in your drawings. I'm going to use this type of connection. And it's going to be an AC1-2-SWC. And the fabricator will know, oh, that's what you mean. So you don't have to write it out all in full. The thing about the online connection tool is it's basically a library, and it's pulling out, it's done all the calculations before, and all you're doing is selecting that particular calculation for that particular connection. So therefore it's limited. You can't do any connection for any design. And you, again, you want to more know about that, I've gone through it in detail on the Daddy Pig website, YouTube channel. There aren't many connection design tools, and even fewer for New Zealand that comply with NZS 3404. Only we had an international standard. That's the trouble with standards, everybody's got their own. This is one of them, Bentley RAM connection. Unfortunately, they're pretty much withdrawing it. Similarly, they're withdrawing a multi-frame. So we have to learn to do something else. And again, it's pulling ready-made examples from a library and putting them together. And so you can choose from the style beam-to-beam connection and so on. So I'd go through this in quite detail, but it's a bit irrelevant if you don't have this software. Right. The Bentley RAM does the same sort of thing. It's pulling from a big library, but it allows you to produce a bespoke drawing, and you can export it in DXF, pull that into your AutoCAD file. It'll also allow you to produce a report, which you can paste into your calculation report. So as has been said, that one of the advantages of steel frame construction is it gives you rapid erection of rigid members. So off you go with your columns and your beams. They come together relatively simply, and you can have simple connections like bolts and cleats. And before you know it, you've got a big steel framed structure. We have to design those connections, but to do that, you need to understand what's going on in that connection. And the forces between one member and another are passed through the bolts in this case. How? Well, the first action is bolt shear. If you put two bits of metal together and put a bolt between them and start pulling on either end, the bit in the middle, the shear plane, will go into shear. So you're putting your bolt into shear. More often than not, your bolts are going to be in shear in the threads. So your threads in your bolt are obviously smaller than the shaft of the bolt as well. And the tendency these days is to use fully threaded bolts anyway, rather than just a bolt with a shaft. The other check you need to do is on bolt bearing. So again, you connect two bits of metal or two metal members, steel members, and put in some bolts. The bolts are transferring their load through the bearing of the metal. So again, pulling on either end puts bearing into the member through that bolt. Right, what's going on? If you've got more than one bolt, more than two bolts, the bolt force distribution gets a bit complicated. So you need to understand what's going on. If you've got a concentric load, it's relatively easy. You just take the load and divide it by the number of bolts. So the force in each bolt, in shear in this case, to the applied load P is just the P divided by the N number of bolts. If you've got an eccentric load, you're putting a moment in that connection, and you need to know how that moment is distributed. So it's quite a complicated thing to work out. The first bit is easy. You split it into two. Take your concentric load P and then distribute that between the bolts, in this case 6 bolts. So the force or reaction in each of the bolts is the applied load divided by the number of the bolts. And for equilibrium, the total forces add up to 0. Now we look at the moment. The moment applies eccentric loads in your bolts at an angle. The sum of the moments applied and reactive have got to be 0 for equilibrium. And the force in each bolt is proportional to the distance from the centroid of the bolt group. So to work out the force in the most eccentric bolt, multiply the moment by the eccentricity or the distance c, and divide it by IP. IP is the polar moment of inertia. And you can simply get that from the square of the distance. Now you're cheating here because you're using parallaxes theorem by ignoring the A values, the areas. And once you've done that, you combine them all together. So that was Bolt's, Bolt force distribution. And we do it again. We do it again for welds. So we take our applied load and resolve it into an applied concentric load with an applied moment. So similarly to the bolt force distribution, your applied load is simply spread over the length of the bolts. So it's R equals P divided by L. Nice and simple. But because we've got an eccentric load, putting an eccentricity and a moment in there. So let's look at that. So as with the bolts, the force in the weld is proportional to the distance from the centroid of the weld group. And it takes a little bit of working out where the centroid of the weld group is. It's a bit more obvious with bolts. But in a similar way, the highest force, R, is the moment multiplied by the distance divided by the polar moment inertia of that weld group. We can split the polar moment inertia or into the X and Y direction, in this case, the vertical and horizontal. And so our IX and IY can be derived from the horizontal and vertical distances. So hence our Rx is the moment multiplied by the distance divided by I. And you combine them together to find out what the total force, the maximum force is in the weld. Hopefully the weld capacity can eat that up without any trouble. Right, briefly, our beam to beam thin plate. And again, you may have a spreadsheet for this, but you probably won't. You could write a spreadsheet. I'll get somebody to write a spreadsheet for it, but you probably won't. We can stop it there. Yeah. If you want to know more about that, there's this version on the Daddy Pig YouTube channel.